Hello, let's talk about math again. Today I would like to talk about the Wiegold conjecture for the small Ree groups. The Wiegold conjecture is a long-standing conjecture and research on it dates back to the 70s, and we have recently shown that it holds for the small Ree groups. And with we, I mean Mark Pengitore, Jeroen Schillewaert and Hendrik from Maldeghem and me, and I want to talk about it today. So let me ask you this. If I give you G, a finite simple group, K greater or equal to 3, Fk, the free group on K generators, is then the action of the automorphism group of Fk on the epimorphism group of all the epimorphisms from Fk to G transitive? This question is strongly related to the Wiegold conjecture, and I thought it might give you a first feeling for what this video is about. So I will not assume that anyone knows what the Wiegold conjecture is. So the first part of this video will be me explaining what the conjecture says and how it is related to the question that I just raised. And after that I will talk about some methods on how to prove it or what is already known and what we have used to prove it for the small Ree groups. And for this video it won't be important to know a lot about Ree groups at all. What we need is the subgroup structure and a geometry attached to the Ree groups. So we know the list of maximal subgroups in the Ree group, that is good, that was known before, and we know the Ree unital, which is the geometry attached to the Ree groups. And these are the ingredients we need, and one can understand all the proofs of our article just by knowing these facts that we also state in the article, and then you can understand it without actually knowing what a Ree group is. But I will, if you have never heard about Ree groups before at all, I will quickly say a word about them now. However, I'm also not an expert in Ree groups at all. So, Ree groups appear in the classification of finite simple groups. They are one of the groups of Lie type, and as far as I understood, if you have G, a simple linear algebraic group, and then F, a Steinberg endomorphism, or also called Frobenius map, and then you look at all the fixed points of G under this F, then you get some finite group of Lie type, and this is determined up to isomorphism by the Dünking diagram that comes with it, by the isogeny type, and by some number that I will not explain right now. And if you have a trivial action on the Dünking diagram, then you get a Schillewaert group, normal run. If you have a non-trivial action and the Dünking diagram has only single bones, then you get a twisted form. And if you have double bones and non-trivial action, then you get Suzuki group or Ree group. And if we look at the Dünking diagrams with double bones, we usually have that B is reserved for the Suzuki groups, and then we have G2 and F4. F4 are called the large Ree groups, and the ones belonging to G2 are called the small Ree groups. And this video will focus on the small Ree groups. And these are usually denoted by 2G2Q, and Q is always 3 to the power of something odd. So that is also why in our article we sometimes write, instead of a Q, we write 3 to the power of 2e plus 1, just because we want something odd in the exponent. For the entirety of this video, K will always be a natural number greater or equal to 3, and Fk will always denote the free group on K generators. Now, suppose we have a finitely generated group G and a normal subgroup such that G is isomorphic to the quotient Fkn. Then we call N a G generating subgroup of Fk. And with that we can define a set sigma k of G, and we call it the set of all the G generating subgroups of Fk, and it's just all these normal subgroups such that the group Fk quotient, the normal subgroup, is isomorphic to G. This set is denoted by sigma kg. And if we now take such a normal subgroup, a G generating subgroup, and we take an automorphism of the automorphism group of the free group Fk, then the image of N under sigma, we can then look at the quotient G and N sigma, and this will again be isomorphic to G. And then we can see that n sigma will again be a G-generating subgroup. And like that, we obtain an action of the automorphism group of Fk on the set sigma kg. The orbits of this action are called TK systems. TK systems were introduced by Hanna and Bernhard Neumann, originally to study presentations of finite groups, but the Wiegold conjecture is also phrased in the language of TK systems. So let's think about it for a second. What does it mean if we only have one TK system? That means that our action only has one orbit. And that means that this action is transitive. So the action of the automorphism group of Fk on our set sigma k G of all the G-generating subgroups. And what does that mean? That means if we have two G-generating subgroups, Ni and Nj, then we can always find a sigma in our automorphism group of Fk such that sigma Ni is Nj. The question that I raised at the beginning of the video was whether the action of the automorphism group of Fk on the epimorphism group of all the epimorphisms from Fk to G is transitive. So what would it mean for this action to be transitive? It would mean that if I take two epimorphisms, pi I and pi j, such that, well, they're in these automorphism groups, so that means they map from F and then Fk quotient Ni, and pi j maps from Fk to the quotient Fk Nj, and both of these quotients are isomorphic to G. And the transitivity means that I can always find an automorphism of the free group, sigma, such that if I compose sigma and pi I can obtain pi j. That means transitivity in this case. If the action of the automorphism group of Fk on the set of G-generating subgroups is transitive, then I also get a transitive action of the automorphism group of Fk on the epimorphism group of all the epimorphisms from Fk to G. And now let me state the Wiegold conjecture. The Wiegold conjecture says, for every k greater or equal to 3 and every non-abelian simple group G, there exists only one TK system. So I hope this explains now how the Wiegold conjecture and the question I raised at the beginning are related. And the Wiegold conjecture is already known to be true for a bunch of groups, not so many, but still a bunch. And I can tell you which groups. And all this time it will always be that k is greater or equal to 3 and p is a prime number. So the conjecture is already known to be true for PSL2p, and Gilman proved that in 1977. For the Suzuki groups and PSL2 2 to the power of m, that was proved by Evans in 1993. For PSL2 3 to the power of p, that was proved by McCullough and Wanderley in 2003. For PSL2 p to the power of r, where r is a natural number and k is greater or equal to 4 in this case, that was proved by Garion in 2008. Then for G is a finite simple group of Lie rank at most r, and k is greater or equal to f of r for a suitable function f depending only on r, and that was proved by Avni and Garion in 2008. And for the alternating groups alt L, in the case that L is less equal than 11 and k is equal to 3, and that was proved by Park in 2001 for k less equal 10. And then for k equal to 11, it was proved by Pak and Cooperman in 2000, but it's not published, but one can find a PDF online. And now we proved it for the small Ree groups for k greater or equal to 5. Now the question is, of course, how did we do that? How was it done before? How can one prove something like that? In the following, G will always denote a finite simple group from now on. And so if we look at this action of the automorphism group of Fk on the set of all the G-generating subgroups, then it's not so easy to work with this action directly. So what we do is we construct a graph such that the action of the automorphism group of Fk on the set of G-generating subgroups is equivalent to the action of the automorphism group of Fk on the vertices of a quotient of the graph that we are going to construct. It will make sense soon. First, we will now move away from the set of G-generating subgroups and move to the set of generating n tuples. So, let n be greater or equal to 2. Then we call a tuple G1, G2, blah blah blah, Gn, a G-generating n tuple if these elements generate the group G. And then we denote the set of all generating n tuples of G by Vng. And of course it's not a coincidence that we call it Vng, because these will be our vertices. Now let's take a closer look at the group out Fk. It is known that this group is generated by so-called Nielsen transformations. That is, if I take two elements, xi and xj, then I can either permute them, so I map xi to xj and xj to xi, or I take xi and I take the inverse, or I take xi and then I can multiply xj either from the right or from the left, or the inverse of xj either from the right or from the left. And these are the Nielsen transformations, and these are generators of out Fk. And now I can also write this down a little bit differently. If I take a k tuple with x1, x2, blah blah blah, xk, then I can map this tuple to a new tuple where I either interchange or permute xi and xj from the tuple, and then I get a new tuple, or I take the entry where I have xi and I take the inverse, then I get a new tuple, or I take my original tuple and where I have the entry with xi, I replace that entry by the product of xi and xj, or xj inverse, where I multiply either from the right or the left, and then I get a new tuple. And going from one tuple to such a new tuple is then called a Nielsen move. And the Nielsen moves are called Rij plus minus, Lij plus minus, Pij and Ij. Ij for inverse, Pij for permuting the entries where I have I and j, then Lij for left multiplication and plus minus regarding the inverse, and Rij for right multiplication. These are the Nielsen moves. And now one can obtain an action of out Fk on the set of k generating tuples of G, and then two generating k tuples are in the same out Fk orbit if I get one from the other via a Nielsen move. And now I can also define a new set Vkg tilde, and this should be the set of all the out G orbits of Vkg. And then we also get an action of out Fk on this new set Vkg tilde. And it is a result of Hanna and Bernhard Neumann from 1951 that the action of out Fk on Vkg tilde is equivalent to the action of out Fk on sigma kg. Now if the action of out Fk on Vkg is transitive, then of course also the action of out Fk on Vkg tilde is transitive. But this action is equivalent to the action of out Fk on sigma kg. And if this action is transitive, that means exactly that G only has a unique TK system. Because the TK systems are by definition just the orbits of the action of out Fk on sigma kg. And if this action is transitive, then we only have one orbit. That means exactly that we only have a unique TK system for G. So I told you we wanted to construct a graph, and we will do that now. So we define a graph. It is called the extended PRA graph. You can look that up. It's a well-known graph, I guess. So we take as the vertices the generating n tuples of G. So the set V and G is our set of vertices. And then the edges will be given by the Nielsen moves. So this extended PRA graph for G is often denoted by x tilde ng. And if this graph is connected, that means that I can reach any generating n tuple from any other generating n-tuple via a sequence of Nielsen moves. And if I can reach any n-tuple from any other n-tuple via a sequence of Nielsen moves, that just translates to the action of out Fn on Vng being transitive. And then we are back to G can only have a unique Tn system. Note that at the point of me recording this, and to the best of my knowledge, it is still an open question whether this last implication is actually in equivalence. So now we have that Tn systems correspond to the connected components of this graph that we have just constructed. And then if we want to show the Wiegold conjecture, we basically just need to show that this graph is connected. So how did we do that, or why did we specifically decide to look at the regroups? The reason is that we read through the articles by Garion and Evans, and we looked at how they proved their results. And they used the structure of the maximal subgroups a lot. Now, the Wiegold conjecture is known to be true for the Suzuki groups, and the list of maximal subgroups of the regroups is kind of comparable to the list of maximal subgroups of the Suzuki groups. So our approach was to look at the regroups and their maximal subgroups, look at the proofs of Evans and Garion, and see how we can basically take these proofs and adapt them for the regroups. Of course, it was not copy and paste. We needed new methods and new ideas, but still we followed a similar strategy. The proof is basically that we start with a generating n-tuple of G, and we show that it is connected to a redundant tuple. Now, what is a redundant tuple? A generating n-tuple of G is called minimal if no proper subtuple generates G, and otherwise it is called redundant. Now, it was shown by Evans in 1993 that if n is greater or equal to 3 and G is a finite simple group, then all the redundant generating tuples of G are in the same connected component of our extended PRA graph of G. So if all the redundant tuples are in the same connected component, and we show that given any generating n-tuple we can connect it to a redundant one, then it shows that the graph is connected. As I said previously, we only showed the conjecture for the small regroups for n greater or equal to 5. The thing is, the longer the tuple, the more possibilities there are to do stuff. And the shorter, the more difficult it becomes to prove it. Note that all finite simple groups can be generated by two elements. And now if k is equal to 2, the conjecture is actually false. There's also a result by Dunwoody that says that for solvable groups, this extended PRA graph is always connected. And there is a result by Bernhard and Hannah Neumann that says for abelian groups, this graph is always connected. In order to show that any generating n-tuple of G is connected to a redundant one, there are multiple steps. So we first show that certain generating n-tuples are always connected to redundant ones. Then we show that other generating n-tuples are connected to one of the ones that we know are connected to redundant ones, so then it's a bit indirect, and so on. I will get more into that later. But for all of these steps in the proof, we use that for the regroups, there's a very nice geometry attached to them. This geometry is called the reunital, and we have that our regroup has a 2-transitive permutation representation on this geometry. And it's a rank 2 geometry. For example, for the Suzuki groups, we do not have such a rank 2 geometry, but for the regroups we have it. And that made some things for us a little bit easier. I will not assume that everyone knows what a unital is, so let me quickly explain it. First, what do we mean by a geometry of rank 2? By that we mean that we have a set P of points, a set L of lines or blocks, and I, a relation. I is then also called the incidence relation, and I is just a subset of P times L. Now, a linear space is a geometry where there is a unique line between any 2 points of the geometry. A linear space is called a unital if there exists a positive integer q such that on each line or each block we have q plus 1 points, and we have q to the power of 3 plus 1 points in total. We can also express it a bit differently and give a little bit more information and say that a unital of order q is a set of q to the power of 3 plus 1 elements having q square bracket q to the power of 3 plus 1 bracket divided by q plus 1 distinguished subsets containing q plus 1 elements called blocks, such that each block is determined by any two of its elements. An example for a unital is the affine plane of order 3. Now, how do we get a unital given a Ree group G? In our Ree group, we have a bunch of Sylow 3 subgroups, and G has a natural two-transitive action on its set of Sylow 3 subgroups. So for the unital, we take as points the Sylow 3 subgroups, and we say that 2 points are contained in a block if the corresponding Sylow 3 subgroups are fixed under a given involution. And of course, one would still have to show that this geometry now has all the properties of a unital, but it has, and it's also called the Ree-unital, and it is also denoted by URQ. And for the following, we always denote points by Greek letters, and if we want to talk about the corresponding Sylow 3 subgroup, then we write P, and then in the index we write the Greek letter. So I told you that we decided to look at the Ree groups because the list of maximal subgroups of the Ree groups is similar to the list of maximal subgroups of the Suzuki groups, and I told you that we will use the Ree-unital. But I have not told you yet about the maximal subgroups in the Ree group, and I will do that now. So we have a whole list of maximal subgroups up to conjugate C. So the maximal subgroups of a Ree group are normalizers of Sylow 3 subgroups. These geometrically correspond to point stabilizers. We have centralizers of involutions. These correspond to block stabilizers. We have Ree subgroups, which are subunital stabilizers. And then we have normalizers of whole subgroups, and these are triangle stabilizers. Which each of these maximal subgroups, we know exactly which orders can occur for the elements contained in them. For example, for the point stabilizers, we know that the elements can only have order 2, 3, 6, or 9. And that is also quite useful, and we use it in our proofs. Now, the maximal subgroups, which are point stabilizers or block stabilizers, are also called structural subgroups. The Ree subgroups are also called subfield subgroups, and the normalizers of whole subgroups, these maximal subgroups, are called small subgroups. Now, the small subgroups are solvable, and by a result of Dunwoody from 1970, we already know that this extended PRA graph for solvable groups is always connected. That means if we now have a generating 5 tuple in our Ree group, where we know that if we take a subtuple containing 4 of these elements and look at the subgroup generated by them, if this is a small subgroup, then that means we can connect this 5 tuple to a redundant tuple. Now a little bit more explanation for that. Suppose we have a 5 tuple x, y, z, v, w, and we look at the 4 tuple x, y, z, v, and suppose that the subgroup generated by x, y, z, and v is a small subgroup, then it is solvable. That means that we know for here everything is connected. That means here, this one, we can connect to a redundant 4 tuple. Let's say the redundant 4 tuple is A, B, C, D. Then we can look at the 5 tuple A, B, C, D, W, which is then a 5 tuple. And our 5 tuple X, Y, Z, V, W will be connected to this 5 tuple A, B, C, D, W. But this 5 tuple A, B, C, D, W is redundant. So this is why everything works out then. Now let's look at the subfield subgroups. The smallest subfield subgroups are isomorphic to PSL28 and PSL28 extended by an element of order 3. If we have a 5 tuple, such that the subgroup generated by this 5-tuple is isomorphic to PSL28. Then we know we can connect it to a redundant 5-tuple because Evans already showed this result for PSL2. If we have a generating 5-tuple X, Y, Z, V and W, and we have a subtuple with 4 of these elements or so that generates something isomorphic to PSL28, then I claim that everything is fine anyway, because if, let's say, X, Y, Z and V generate something isomorphic to PSL28, then by the results of Evans we know that the graph here is connected, so we can connect this 4-tuple to a redundant 4-tuple. Let's call the elements of this redundant 4-tuple A, B, C and D. And then in our case, where we want to look at the 5-tuples, we can then look at the generating 5-tuple with A, B, C, D and W, and we can connect our original tuple to this one. This one will again be redundant. So in this case we are done. If we have a subtuple generating something isomorphic to PSL28, then with the results of Evans we are done. If we have a sub 4-tuple generating something isomorphic to PSL28 extended by an element of order 3, then it is slightly more difficult, but not so much. In that case, let's call the group that this 4-tuple is generating, let's say the 4-tuple is X, Y, Z and V, and the group generated by these elements, we call it H. Then we can write H as H0 extended by some Xi. Xi has order 3. This is just how we have our notation now. Now I claim that if I consider the element x to the power of I, y, then this will be for some I in the set 0, 1, 2 fully in H0. So if we look at some element x of H, then we can always write it as x prime xi to the power of some I, because this is just the structure of the group H. Every element we can write like this, where x prime is the part that is in H0 and then xi to the power of something. Now if we write out our element x to the power of I, y, then we have x prime xi to the power of I, y prime xi to the power of j. This is just the same thing written out, and now x prime and y prime are the parts that are in H0. Now we do the thing where we do a plus minus 0 thing, and we write it as x prime xi to the power of I, y prime xi to the power of minus I, xi to the power of I, xi to the power of j. Now x prime is in H0, y prime or xi to the power of I, y prime xi to the power of minus I is also in H0. So we see that the only thing that can make our element not be in H0 is xi to the power of I, xi to the power of j. And now we can go through the cases. If j is 0, then xi to the power of j is the identity. Then we can choose I to be 0, then also xi to the power of I is 0, so then xi to the power of I, xi to the power of j is 0, is the identity. So this is all fine. Now if j is either 1 or 2, we can choose I to also be either 1 or 2, but such that I is not equal to j, and then the sum I and j will be 3. And then of course if we look at xi to the power of I, xi to the power of j, it's the same as xi to the power of I plus j, it's the same as xi to the power of 3 in this case, and then it's just the identity because xi has order 3. So in either case we can always find some I such that the element x to the power of I, y, is in H0. And now we can replace our y by y prime, and we define y prime to be x to the power of I, y. And we can do the same for z and v. And then we have a 3-tuple y prime, z prime, v prime. And all these y prime, z prime, v prime are contained in H0. So what they generate will be a subgroup of PSL28. And by the classification of subgroups of PSL28, we have that this will either be solvable, and then again we can use the result by Dunwoody for solvable groups, or it will be PSL28, but then we can use the result by Evans again. So if we look at the 3-tuple y prime, z prime, v prime, we can connect it to a redundant 3-tuple. And then we can go up again and see that our 5-tuple can be connected to a redundant 5-tuple. And this is how this is done. And then for the larger subfield subgroups, it also follows with calculations. The calculations involve looking at the orders of the element and what can divide what and stuff like that. But I will not talk about this right now. Basically my point is, for the small subgroups and the subfield subgroups, let's say we are good for now, but then we still have to deal with the structural subgroups, so the point stabilizers and block stabilizers. But then for those, it's really nice to have this Ree-uniter. So let's now look a little bit at the point stabilizers. If we have a Silo3 subgroup in our Ree group, then for an element of this Silo3 subgroup, we can also say a lot about what it does in our Ree-uniter. First of all, the elements of a Silo3 subgroup can either have order 3 or order 9. But there are two different kinds of order 3 elements. There are the ones which are in the center and the ones which are in the derived group but not in the center. And then the elements of order 9 are basically the other ones. The elements of order 9 and the elements of order 3, which are in the center, both have no fixed lines. But the elements of order 3, which are in the derived group but not in the center, they stabilize Q lines through the fixed point and act without fixed points everywhere else. Let me give you another property of the Ree-uniter. But maybe let's first talk about the Hermitian uniter, which is kind of like the prototype of a uniter, and then we can compare. So in a Hermitian uniter, we have these nice central collineations. That is, automorphisms of the uniter that fix a certain point, stabilize all lines or blocks through that point, but then have a sharply transitive action on the points of a line, of course without the fixed point. Now in the Ree-uniter, what we have is we fix a point, we stabilize Q lines through that point, then with the other lines we interchange them, and we have a sharply transitive action again on the points of these stabilized lines. I will include pictures. I didn't say it so exactly, but in the picture it will become clear what I mean, I think. And in the Ree-uniter, it's actually the case that if we take a point and then a collineation that fixes that point, then we can look at all the lines or blocks through that point, and then we get those which are stabilized and those which get interchanged. And this gives us a partition of the lines through a point. And that is a very special property here that we have in the Ree-uniter. Another special property of the Ree-uniter is that if we take 2 points and we look at the partitions of the lines through these points, so we have through the one point Q lines that are stabilized and through the other points Q lines that are stabilized, and we now only consider these lines, then every one of these lines here, so the one point, intersects exactly one of these lines here, so the other point, in exactly one point. But this only is true for the lines that are stabilized through that point. But then we always have a unique line intersecting in a unique point. Again, I think it is probably easier to see it in the picture. It is more difficult to put it into words, but it's a very special property and we actually also use it later. What I would now still like to do is to show you a proof sketch of a proposition of our article where we use some of the properties of the Ree-uniter, such that one can see how we use them. and it's all about getting rid of subtuples generating structural subgroups. So suppose we have a generating 5-tuple with elements x, y, z, v and w. And suppose we will now narrow down on a special case because, I cannot prove all the things. So this is just an example now. So suppose they all have order either 2, 3, 6 or 9. And now we can already try to get rid of order 2 elements. And for that, first assume all of these elements x, y, z, v and w had order 2. So assume they are all involutions. If they were all commuting involutions, they would generate an elementary abelian group of order 32. But this cannot be a Ree group. And these elements are supposed to generate a Ree group, so this is a contradiction. If they are non-commuting, then we can at least find some element of order 3. For example, xy, if we multiply that. And then we can replace in our generating 5-tuple y by xy. And then we have a new generating 5-tuple that is connected to our previous one. But here we don't have that all of the elements in the 5-tuple are involutions. And then, conveniently, in our article we have a lemma that says as soon as one of the generating elements is not an involution, then we can get rid of all involutions. So this is how our first step here, basically. I know this might be not so satisfying because I used this lemma in our article, but I cannot explain every proof in our article. So this is just a little thing here. So now we got rid of involutions. So now we have a generating 5-tuple where we may assume they all have order either 3, 6 or 9. And what is nice about elements of order 3, 6 or 9 is that they all fix a point. And we will now denote the points that they fix by alpha, beta, gamma, delta and alpha, beta, gamma, delta, psi respectively. So x fixes alpha, y fixes beta and so on. And the next thing we want to do is we want to argue why they don't all fix the same point. But that is quite easy because if they all fix the same point, so alpha equal to beta equal to gamma, blah blah blah, then what x, y, z, v, w would generate would be a point stabilizer. But our Ree group contains point stabilizer, but it is not a point stabilizer. So this is again a contradiction to the fact that our 5-tuple generates a Ree group. So now we may assume that they do not all fix the same point. So we may assume, let's say, alpha is not equal to gamma. Remember that the whole goal here is to get rid of subtuples generating structural subgroups. Structural subgroups were the ones that either stabilize a block or a point. That means that we have to somehow get from our original 5-tuple to a 5-tuple where the elements do not share common fixed things. So now we already noticed they cannot all fix the same point, but we want to get them further apart, let's say, in the way that what they fix should be different. So suppose alpha is equal to beta. We said we may suppose that alpha is not equal to gamma, but suppose now alpha is equal to beta. Then we look at the element z inverse yz. Suppose this element fixed beta. Then we would start with beta, do z inverse, map it to some beta prime, then we do y, map it to some beta prime prime, and then we do z, and again, because we assume that beta is fixed, we land on beta. Now if z inverse maps beta to beta prime, z has to map beta prime to beta, which means that beta prime prime has to be equal to beta prime. So y fixes beta prime. Beta prime is the image of beta under z inverse, and this cannot be equal to beta because otherwise z inverse would fix beta, but Z inverse only fixes gamma. And since Y only fixes beta, we get a contradiction here, because Y cannot fix both beta prime, which is not equal to beta, and beta. It only fixes beta. So this is a contradiction. That means the element Z inverse YZ does not fix beta. So we have now found this element Z inverse YZ that does not fix beta. And we can, because we only did Nielsen moves, right? We took Y and we multiplied Z inverse from the left and Z from the right. So we can replace in our generating 5-tuple Y by this element. And then we have a new 5-tuple where we have X, this new Y, Z, V, W. And now we have that the element that the new Y fixes, let's call it the new beta, is different from alpha. Of course, what we did to Y now, we can also do to other elements of our generating 5-tuple. And then we can already achieve that if we look at X together with some other element of our 5-tuple, then the subgroup generated by these two elements will not be inside a point stabilizer, because we can now assume that all our elements fix a different point. And that already brings us closer to our goal of getting rid of subtuples generating structural subgroups. What happens next in our proof of this proposition in our article is that we again separate into different cases, and I will only talk about one case in this video now, and that is a case that in our generating 5-tuple with the elements X, Y, Z, V and W, we have that all of them have order 3 and are non-central. That means they all stabilize a block through their respective fixed point. And again, we may assume that they do not all fix the same block, because if they did, what they would generate would stabilize a block, but they are supposed to generate a regroup and not just a block stabilizer. So again, we may assume that at least 2 do not stabilize the same block. So we may assume that gamma is not in the block with alpha and beta. And what we get then as a picture is a triangle where we have as the points alpha, beta and gamma. And this should remind us of the picture that I showed when I talked about this very special property of the Ree-unital, where if we have a stabilized block and 2 points, and we look at all the Q blocks stabilized to the one point and all the Q blocks stabilized to the other point, then each of one of these stabilized only intersects one of the other stabilized in exactly 1 point. And so what we can see here now is that X will stabilize the block with alpha and beta and with alpha and gamma, but it will not stabilize any block that goes from alpha to some other point on the block with beta and gamma. And here we exactly use this property of the Ree-unital that I said is so special. But now if we basically do the same trick again, where we look at the element Z inverse YZ, then this element will have its center on the block with beta and gamma, but not beta and gamma. So somewhere on there, excluding beta and gamma themselves. So this element will have the center somewhere there, so it will be some point that is not, whose join with alpha is not a block stabilized by X. And that is exactly what we want. So if we now replace in our generating 5-tuple Y by Z inverse YZ, then we get that, well, if we look at X and the new Y, then what this generates is neither a point stabilizer, because we already excluded that in the first part of our proofs, nor a block stabilizer, because we just got rid of this option right now. So now we have that this does not generate a structural subgroup, and this is exactly what we wanted. And now we can again do the same procedure for other elements of this generating 5-tuple, and then we can already get rid of a lot of subtuples generating structural subgroups. And then of course one has to go on and still prove all the rest, and I will not do that because it's too long for this video. but I hope that gives an idea how we use these properties of the reunital and how our proofs go in general. I hope I could introduce you to this conjecture and explain a little bit about why we looked at it, why we looked at the regroups, how we approached this whole thing and what we used, and give you some idea on how some of the proofs might go. In general, there's a lot of research, not only about this conjecture, but also about these extended PRA graphs. And there's a survey article by Lubotzky that talks a lot about also generalizations of this conjecture and what is already known, etc. And if you are interested, then I highly recommend to read the survey article. And this was all I wanted to talk to you about, and thank you very much for watching, and goodbye.